going to talk about what is called a regression line. A regression line. Okay? Now, to give you an idea of this before I move on, remember last time I showed you how to plot a scatter plot. Okay? So if you have one set of x values and one set of y values, and if we say we have paired data, right? So for each x, there's a y that goes along with it, right? That was what we said. The first time we started talking about two sets of data in Chapter 9, we talked about independent. But then we said, okay, let's have the pairs matched up. And if you do, you can plot the points, right? You can plot the points. And so we got a picture of, you know, points. So each point has an x-coordinate and a y-coordinate. And you guys did this in algebra class. I don't know if this would be x1, y1, and x2, y2, or, you know, you could actually put numbers in there too, but you could plot points. By the way, looking at this right here, do you think that r is closer to 0 in this example, or 1, or -1 in this example? Talk this out with someone next to you for a minute. Make sure you guys agree. So what are we coming up with? 1? How many are saying 1? And you're right. Because I can see, even though it doesn't line up exactly, it looks linear. Right? It's close to lining up exactly. Not quite. And I can see also that it has what's called a positive slope. Now there's an algebra word that we're going to come back to again. Slope. Tell me what you guys know about slope. Anything? Yeah. Rise over run. And I heard someone say y equals mx plus b. This is the equation of a what? Of a line. Yeah, when you have a line, its equation looks like this. And which letter in here was the slope? It's m. It's the number in front of x. Okay? So this may be, you know, causing nightmares to some of you, but it's coming back, and so I want to make sure I review it here with you. I don't want to just spring it on you. I want to say, okay, you've seen this before. Just let's remember. Now here's the deal. What we'd like to do is we'd like to write kind of a rule that describes the relationship between x and y. If you're saying that r is close to 1, you're saying that the x data and the y data are related. That's what you're telling me. And I can even see it. I can see the relationship. So what we do is we try to come up with a line that kind of goes through the data. Best fit line. There's the word. Regression line, another name for it. Give me a second. It's also called a best fit line. Or you may see the word least squares. All these are talking about the same thing. Okay? And what we do is we try and get a line that is pretty close to the points. We minimize the error, the residual it's called. And then what we'd like to do is write an equation of that line. And it's going to be in this form. So that's the game, is how do we do that? Okay? Now, David, you had a question. Slope is m. I heard someone else mention this old formula, and they're correct. Change in y over change in x. I don't know how much of this I'm actually going to be using, so I'm not going to go crazy here. Okay? You've done that in another course. All right, now, what do I want to do? I want to give you the regression equation. given a collection of paired data, the regression equation is given as follows. You notice it looks a lot like what I just wrote, doesn't it? The y, your book is going to put a little hat on top. And that's telling you, hey, wait a minute, guys, this is a regression line. Okay? When you see that little hat, you'll think, oh, this is a best fit line. This is a regression line. Somehow it describes the relationship between the two variables. Which two variables? X and Y. Now you'll notice they have B here twice, right? B0 and B1. One of those is the slope. Do you know which one is the slope? B1 is the slope. Because it's in front of the what? It's in front of the X. B0, that's the y-intercept, if you want. Why our book decided to write it this way, I have no idea. But they did. Okay. The graph of the regression equation is called the regression line or line of best fit or least squares line. I already gave you all those words. All right. That's fine. Now, notation. Yeah, come on up then. That's funny. Okay, hang on. The notation you want, notice again, once again, there's a difference between population and sample, right? Population and sample. And the difference is we use the normal letters for which one? It's been all semester long. Sample, and we use the Greek letters for what? Population. So you take a look at what they did. Here's the equation I just gave you. Y equals B0 plus B1x. And by the way, this hat, this ought to be up here. Y hat. Okay, that's the regression equation. Now, the equation of the regression line for a population, we'll write Y, and will we write Y hat? Maybe not. But I won't need the hat. But you notice the big difference is that instead of B's, they're going to use the Greek letter B, which is called beta. Okay, it's kind of a slanted looking B. So if you see betas, they're talking about a population. Okay. Well, kind of like we had P and P hat. Remember, P hat was the estimate. So same thing here. Y hat is if you want an estimate of the actual line. So let me show you. In the example we had, I had some data like this, right? And I plotted a line through it. Let me do that again. Okay? So let's say that's the best fit line. It doesn't look like it to me, but let's suppose it is. Now, do you think I plotted all the data that's in the population? No. Let me do it. Let me plot all the data that's in the population. Okay, there's all the data that's in my population, let's say. This is not notes you could take. You can only watch. I understand that. Okay. If I did the best fit line for the population, looks to me like it'd be something like this. Right? Is that the same or different than the blue line I drew initially? Different. Now, why is it different? Well, because I had a sample of this data. I'll highlight it in black for you. My sample was like this, right? And so based on that sample, I did the best I could. Now, is the sample line close to my population line? Well, kind of. This is a very extreme example where it's worse than it'll usually be. But the idea is you're estimating the equation of the regression line for the population by using a sample. And we've been doing that. That's what statistics is. Kate? absolutely. You could have yeah, yes, you could. Yeah, how would I have a vertical line? I guess I don't think you're going to run into that anyways, so I wouldn't worry about that. Okay. Those are good questions. Okay. Requirements in order to do this. And again, what's my main point? Everything we do has requirements, right? So we'll go quickly through this. The sample of data is a random sample of quantitative data. And notice it's paired. That's the big idea here, I think. Right? You need the x's and y's to be paired. Notice what it says we want to do. Visual examination. They showed an example last time where the data looked like this. Remember that? You guys remember that example? If you get that, do we want to do a line? No. Okay? You really ought to take a look at your data in addition to using the formulas. It says any outliers must be removed. Can you tell me what an outlier is from earlier in our course? Something that's way off the center was a definition we had. Yeah. What else? Yeah. Let me show you an example of an outlier. Suppose I had this kind of data. Doot, 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 doot. And then, nah. That's an outlier. Do you see how it doesn't follow the pattern? Okay? And the problem is, if you graph a best fit line with that outlier, you might get something like this. Because you're trying to minimize the error for all the points. And so then you say, well, wait a minute. Maybe the whole problem is that some bozo dropped half of the sample, right? If you see something called an outlier, you probably don't want to include that when you're going to do your regression line. Okay? Now, there are formulas in our book. Formulas for slope, formulas for y-intercept. And I'll probably show you in an example how we can use these formulas. I think we'll take one from your homework last night and work with it. Okay. Let's see if we can read what this says. Okay. So remember, B1 is going to be actually M for us. That's the slope, right? It says B1 equals, well, notice it's related to what? R. What was R? Correlation coefficient, right? R could be anything between -1 and +1. Scott, that's not nice. Now this S, what does the S stand for? Sample standard deviation. Now why do they have this little Y down here or this little X down here? You want to know which one it's coming from, right? We're going to need to know standard deviation of two different samples in order to compute the slope. So what's the idea? The idea is, first, we compute the slope. Then, compute the y-intercept. And that's what Formula 10.4 is telling you. Notice, you can't do Formula 10.4 unless you already know the slope, right? So if you have y equals mx plus b0, we're calling it, and you say, okay, I want to get b0 by itself, what do you do to both sides? Subtract mx. That's all they did. And so they said b0 equals y minus mx. This is exactly this formula. B0 equals y minus mx. thing you'll notice, which x and y did they use here? They used x bar and y bar. What are x bar and y bar? The mean of each of those. So we needed the standard deviation of each data set to get the slope. And then, because we have so many different data points we could use, we used the mean in each case, the sample mean, in order to get the y-intercept of the regression line. Okay. Now, important to know, calculators or computers can do all this. Okay? Which is nice. And we'll definitely take advantage of that on the homework and go from there. The special property is that if you use these formulas, the regression line fits the sample points better than anything you could do by hand. Okay? So if I give you some points and I say, okay, what's the best line to go through them? Follow those formulas and we can prove mathematically that the regression line fits these sample points the best. And by the way, just to give you an idea, every year students here at Lakeland in my Calc 3 class prove this. So if you take 3 semesters of calculus, you can go through and show that, oh, this regression line is going to be the best one you can do. So it takes some work to get there, but we're going to go ahead and use the formulas anyway, because no matter what field you're going into, the regression line is something you want to know about. Okay. What about rounding? 3 significant digits. Oh yeah, please don't round intermediate values. Some of you guys on the exam, even that was something where, you know, you have this beautiful calculator, but then you round up and then write something down on paper, and then what will happen is it'll affect your final answer. And I guess the point is that when you're doing a regression line, it'll affect your answer more than some of the other formulas that we've had. So you really want to be careful not to round the intermediate values when you're using these formulas. What's that? I'll show you in my example. I'll show you. That's a good question. Okay, so here's an example. This is right out of your book. Yeah. Should I do this, or would you rather see a homework? Oh yeah, that's all in there. What's that? Okay, well, we'll try this, and then if you want another one, we'll do another one. I'll go from your homework next. Because I do want to talk about the homework you guys did for today. Okay, so it says, let's look at the Chapter 10 problem. And you guys looked at this already, right? We looked at the pizza versus what? Subway fare, right? Look at that. Cost of pizza, cost of Subway fare. Is it the same? Well, almost every time. Not quite, right? In 95, it was different. 2002, it was different. But other than that, there we are. CPI, what is that? Is that in your book? Better pause. I guess somehow the CPI, the Consumer Price Index, tells you something about how inflation has affected life, right? I mean, in 1960, whatever this set of goods is didn't cost as much as it does in the 90s or as much as it does in the 2000s, right? That's what this is saying. All right, fine. Now, are the requirements satisfied? Yes, we have a simple random sample. Does the scatter plot approximate a straight line? I guess I should check that, huh? So we could do that. And are there no outliers? Well, yeah, we could do that. Again, your book gives you different options for technology. What are the ones we've used? We've used StatDisk, we've used Excel, but most of all we've used the TI-83. And did you guys use this when you did the homework for today? The linear regression t-test. Did you guys use that? Did we do the homework for today? Raise your hand if you did the homework for today and used that. Okay, so a few people did. I mean, that was the suggestion, is that's what we want to do. And when you do that, you get all kinds of stuff coming out, right? Well, yeah, I should show this to you. We'll do a homework problem together. Yeah, I'll do a homework problem to you. But I guess what I'll show you here is how you read this, okay? So it says here that y is a plus bx. It says here that a is 0.0345 blah, blah, blah. Now, by the way, and it says that b is 0.94. When you go to read this, which one of these is the slope? Why did you say b? Yeah, the number in front of x is the slope, right? So according to this, we have a line whose slope is about 0.95, right? So m, the slope, your book calls that b1, is 0.95. And it says a is, well, 0.03, which is pretty close to 0. So, you know, our line goes through 0.03 and has a slope of 1. So if you remember your algebra, your line's going to look something like that. Okay? And then here it gives me what's called r squared. Now, of course, yesterday we had r. So I guess you could take the square root of that. But I think if you click the down arrow, it'll give you more. But notice r squared is pretty close to 1. So that tells you this data lines up pretty well. Okay? Yeah? Yeah, so I have to show you how to do that. So I'm going to get to the example. But anyways, all of these technologies show that this is your equation. Y hat, they should put the hat up here, is 0.0346 plus 0.945x. Okay. This is an estimate of what's called the true regression equation, meaning this estimate is on some sample, right? But if you took another sample, do you think you'd get the exact same equation? No. I mean, when we say it's a sample, let's look at that again. Where's the sample? Oh, here it is. How many years did we pick? 6 years. So n equals 6, right? But what they're claiming is maybe that models what has happened in all the years. Okay. So that's the idea. Another sample drawn from the same population would probably lead to a slightly different equation. Okay. Now, let's graph this on the scatter plot of the pizza subway fare and examine the graph to see how well it fits the data. On the next slide, they used a software called Minitab to show you what it looks like. But yes, you can do this on the calculator. So here we go. Here are my 1, 2, 3, 4, 5, 6 data points. See that? And then here is the graph. Well, that's the equation of the red line graph. Of course, you notice, it's kind of funny, they say subway equals this. So it's y equals, and again, this would be b0 plus b1x. And I would put y hat because, again, this is a sample. You guys follow that? So what do you think? Does it fit the data pretty well? Yeah. Okay. Now, use the regression. Why do we do this? Sometimes we do this to make a prediction. So, for example, if I go back to the picture, can you tell me what these green dots represent again? I remember the first one was 1960, right? And we had, let's see, cost of a slice of pizza was 15 cents, and the subway fare was 15 cents, right? And then over here somewhere, the most expensive we had, they were each $2. So what you might say is this: hey, I wonder what happened when the subway fare, which is my y value, was 50 cents. What do I think the x value was? Okay. Well, a real mathematical way to figure that out would be to use the equation. Okay? You could put your 50 cents in for the subway. Put the other numbers in, and then just leave the x here, because the x is the thing that's unknown. And you could solve algebraically for that x. Does that make sense? And what you'd be doing is you'd be finding the coordinates of the point right on that red line. And then even if you don't have the data for a time when the subway fare was 50 cents, this line can give you an estimate. It helps you to fill in the gaps. That's the idea of a regression line. Now, oh yeah, please. Let me go ahead and pause. Again, back to what we're doing here. You should only use the regression equation if the graph looks good, okay? If you have a line that doesn't fit the points very well, then you shouldn't use that line. Could be because of outliers. Could be because there's not really a linear relationship. Maybe some other kind of relationship. Yeah, make sure that R is either close to 1 or negative 1. Don't do it if R is close to 0. That'd be a problem. Oh, use the regression line for predictions only if the data does not go much beyond the scope of the available sample data. See, you can't predict too far into the future, or you may get yourself in trouble. Like I could ask this: hey guys, when pizza costs $10, what do you think the subway fare is going to be? Well, a naive person might say, well, $10. But see, that would be if the pattern continued linearly. And statistically, you don't want to do that. You can get yourself in big trouble doing that. Okay? It's funny, though, too, because I've taught many, many algebra courses where they do exactly that. They say, if this pattern continues, what would happen? And that's fine, but there's no reason I should think that the linear pattern should continue. If the regression equation does not appear to be useful, then the best predicted value of a variable is its point estimate, which is its sample mean. So don't forget that we already have a way of making an estimate. This is another way of making an estimate, a regression equation. But we also have sample mean. And that's sometimes the best you could do. Matter of fact, that's what you guys were doing here when you guys said, I want to stay near 100. Because that's the mean. So those of you that said that, that's very sound advice. Okay, this is in your book. It says, you're trying to predict the value of y. What do? Well, do you have a good regression equation? Then use it. If you don't have a good regression equation, then what's the best you can do? Y bar. What's Y bar stand for? Sample mean. So if you have a good line, use it. If not, use Y bar. How do you know you have a good line? Look at the graph. And are not near what? When do you have a bad graph? When it's near 0, right? So you want to be away from 0, either close to 1 or negative 1. Then you're okay. You're off. I already talked about this. Yeah, I kind of want to finish up with a problem. Can you pick a homework problem for me? People that did the homework, let's take a minute to do that. So remember when we covered last time regression, the slope is related to R, right? R was what? Correlation coefficient, right? We computed that in section 2. And then this SY and SX, those are what? Standard deviations. Okay, so if you have R and the S's, then you can actually get the best fit line. Thank you. And I said calculators or computers can compute these values for you. And we're going to take full advantage of that because I mentioned to you last time, you need Calc 3 to really understand how this works. And we're not going to get there this semester. Okay. Now, did I talk about rounding? Oh yeah, I guess so. I did that. Yeah, then we did the pizza problem. So I wanted to get to an example from the homework. So I'm thinking about problem 15. So let's look at it. Problem 15. So actually, this is the same problem 15 you did from section 10 too, isn't it? Take a look at it. What page are we on? Say 10.3 is what we're on. 549. So I guess my question is, does this look familiar to you? Right arm versus left arm? Does that look familiar to you or no? Maybe we didn't do this. Maybe we stopped at 13. We stopped at 13. Okay, so let me see what we have here. Let me show you what we're doing here. We have a little chart of some blood pressure measurements. So this is part of a study. They did some blood pressure measurements. Same, they take a woman and measure blood pressure from the right arm, and then they measure the blood pressure on the left arm and see how they compare. And how many people here have taken someone's blood pressure before? I know we have a number of you. Okay, you have to let me know if this happens or not. So this person in the right arm, that we got a 102, and in the left arm we got a 175. And in the right arm we got a 101, and in the left arm we got a 169. And in the right arm we got a 94, and in the left arm we got a 182. And in the right arm we got a 79. Does this worry anybody? Yeah. In the left arm we got a 146. In the right arm we got a 79. And in the left arm we got a 144. All right. Actually, we better turn back to section 2 then. Okay. So flip back a few pages, because they say a little bit more about this study in section 2. Here they give you a source. Listed below are systolic blood pressure measurements in millimeters of mercury obtained from the same woman by somebody in the Archives of Internal Medicine. Okay, so this is one particular woman. Page 532. Problem 15. I don't know. It says here that we took 5 measurements, huh? And actually what it says we want to do here is a couple things. We want to construct a scatter plot. So this is really the 10.2 instructions. See, 10.2 and 10.3 are closely tied together. So I think I'll do 10.2, and then we'll talk about what you're going to do for 10.3, because 10.3 is the homework that's due, for example, next Tuesday. Okay. So you construct a scatter plot, and then we want to find R, which is the what? The correlation coefficient. Then find critical values of R. Okay. And again, here they tell me my significance level. Just amazing to me how this stuff is all meaningful to you now, compared to a few weeks back. I could have written all this, you'd have been looking at me like, huh? Some of you still are saying, huh? I hope not. Anyways, okay. And then it says, determine whether there is sufficient evidence to support a claim of linear correlation between the two variables. Claim. There is a correlation. Between what and what? Right arm and left arm. even in this woman who has very strange blood pressure results. We claim there's a correlation. Now, this is a different kind of claim than, most of the claims we've been testing, right? So we just want to maybe review again how you do this. Okay, so let's get out the calculator here. And actually, I think this is what, Shelley, you were asking about this. How do I do this with the calculator? Okay. There you go. Okay, here's my calculator. Now, remember how to get that data into the calculator? You can go ahead and start that if you know what you're doing. Hit the stat button. Yeah, and then edit so we get those lists. That's right. Hey, that was fast. Oh, I had to do something while you guys were talking about all these papers. All right, so I got the data in there. Give everyone else a minute or two to type in if they want. I'll pause it in the meantime. While you guys are typing in, I'll just review a couple things we talked about. I showed you guys how to make a scatter plot, right? Want a reminder of that? Okay. Hit the second key and then the y equals. Not just y equals. Hit second y equals. And you can turn on different kinds of stat plots. So I'm going to click on and enter once I'm on plot 1 here. I want to turn it on, so I'll press enter to turn it on. You have to tell it what type you want. We've used histogram before, but we want scatter plot. You tell it where your X list and your Y list are. Mine are in list 1 and list 2. And once you do that, you're pretty much ready. The only thing I have to do to graph it now is press zoom, and then you have to find zoom stat. And I figured out last time I did this, if I go up, I get there faster. For me, it's choice 9. But I don't know what it is for you. Okay, and if I press enter, there's my data. So it's interesting because if you look at the numbers, they don't necessarily tell you the same story as the picture here. Let me click the trace button so I can go through again. Okay, so there's 102, 175, and I'll click to the right. There's 101, 169. There's 94, 182. There's 79, 146, and 79, 144. Right? Those are the 5 data points, data values. But a picture really tells you a lot, I think. Now, what do you think? Do you think there's a line that goes through this data in a nice way? Is there a linear correlation? That's what we're going to try and figure out, right? Okay, so I'm going to do this. I'm going to hit, I want to do the linear regression t-test. You guys have seen me do that, right? Where do I find that? Hit the stat button and go on over to tests. By the way, that z-test, I don't know if any of you have tried using that yet. Yeah, we did all that stuff in Chapter 8 on hypothesis testing. There's a z-test and a t-test sitting right here for me. If I figure out how to use them. Oh, hit the stat button. But you have to move over to the right. If you move over one place to the right, we've been here before, calculate. But if you move over 2 places to the right, these are all the different kind of tests you can do. Hypothesis testing. That's what it really is. Okay, so what do we want to do? Again, hit up key to get there faster. We want choice E, the linear regression t-test. I'll hit enter. And it says where is your X and where is your Y? And for me it's in list 1 and list 2, so that's all good. And I'm just going to go all the way to the bottom and hit calculate. And let's see what happens. Well, a couple things happen, I guess. Notice one thing is it gave me a p-value. P equals 0.056994, right? What's that p-value tell me? That's above my alpha. Yeah, that's what we want to compare p to. So p is high. The null must fly. Now, what's the null? Well, that's kind of confusing, I guess, right? Claim. There is a correlation between the right arm and the left arm. Okay? So here, I guess that would be my original claim. Yeah, so the book doesn't really write it this way, right? But this is kind of my H1 in a sense. There is a correlation. Yeah, I don't know if I want to do that. This is R, right? R is called the what? Correlation coefficient. By the way, did it give me the correlation coefficient? Let's look at it again. I think it did. I guess I have to go down to get it, don't I? It gives you R squared, but it also gives you R. R squared will be important also. But R is 0.8670. Okay, so I have 0.867. Okay, and the scatter plot I did. Did it. So I'm done with that. Find the critical values of R where alpha is 0.05. Now this is where you can use that pull-out card. Remember that? There's this table A6. Let's get that out. And then I'll go back to what I'm talking about with the hypothesis test. So let's see. This alpha equals 0.05 tells me I'm in the first column. And, oh, what about n? Do we know n? Oh yeah, n is 5. So the critical values well, this isn't degrees of freedom, this is just n. This is just n, yeah. So n is 5. So my critical value is 0.878. You guys find that? Okay. So and again, yeah, like I said, they gave me a p-value also, but if you look at it this way, okay, what is the possible range of R? R could be anything between what and what? Do you remember? -1 to 1. And when you're at 0, that means, do you remember what 0 means? What happens if R is 0? No linear correlation. Right? Now, what do I have? I have a critical value. My critical value is right here. 0.878 is my critical value. And -0.878. Right? So these are what you call your critical regions. So you look at your test statistic. If your test statistic is in the critical regions, you'd say there is a linear correlation. If your test statistic is here, you'd say there's no linear correlation. Where's our test statistic, our R? Well, for us, where did R end up? 0.867. That's about right there, right? Well, again, here's the way I look at it. I know for 0 there's no linear correlation. If I get 0, there's no linear correlation. So the inside region has no linear correlation. Since 0.867 is on this side of the critical value, there's no linear correlation. Does that make sense, John? Okay. What would happen if you got something out here? Then you'd say there is a linear correlation. Okay. Yeah, that's what we're saying. And, you know, it's kind of interesting what you're doing here, really. What parameter are we testing with this claim? Right? That's the real question. Because I understand hypothesis testing by this point in the course, or I dropped out, one of the two. Right? I understand hypothesis testing at this point. I understand that there's a claim about a parameter. Parameters are Greek letters, right? And I'm testing it with my statistic. What's the statistic we just learned about? It's R. Now, what does R relate to if you go to the Greek? Well, there's something called rho. That's the Greek R. What's that? Rho is an R, but I guess it looks like a P almost. Oh, you're talking about beta. Beta's in 10.3, and we'll get to that in a second. So this rho right here is really the deal, okay? So what parameter are we testing? Well, we're testing either this is true or this is true. Now, one of these should mean something to you. What happens if rho equals 0? That means no what? Linear correlation. That's what I was talking about up there in that picture. If rho does not equal 0, that means there is a linear correlation. Okay? So back to what we did. By the way, what kind of test is this? One-tail or two-tail? Two-tail test, right? That's why this picture you saw the two little critical regions. When we computed the p-value on the calculator, what did it give me? It gave me p was 0.578 or 0.0578 or something like that. Is that low or is that high? P was high. So that means let the null fly. Now, here's the question. I didn't word it this way before, but I'm going to now. What was the null hypothesis of this whole problem? Rho is 0. Yeah, that was the null hypothesis. This is H0 and this is H1, right? So we decided there was no linear correlation. And it really is just another hypothesis test. Now, I don't care which way you do these. If you want to think of it as a hypothesis test, fine. If you want to do it the way I suggested up here, I'm fine with that too. Okay? As long as you can understand how to compute it. Like I did right here? Yeah, you could do that. And that'll get you the answer. Yes, Craig. Yeah, that was our test statistic. That's right.
Lower, so
lower than what?
than our critical value.
Oh, but that's not how critical values work.
Okay, yeah.
How do critical values work?
Then you reject it.
If it's in the critical region, you reject. And this time it wasn't. That's right. So low and high is when you're using p-values. But if you're doing that, then you got to see if it's in the critical region. That's why I drew the picture. The picture helps, for sure. Okay, now, back to 10.3. They give you the same problem in 10.3 on page 549. Same data. What do they ask you to do? Well, let's look. In each case, find the regression equation letting the first variable be x, so the second variable is going to be y. All right, so this isn't too hard because technology did it for me. What's that? Same problem. Problem 15 again. They give you the same exact problem. Right arm, left arm. So the data is already in my calculator. Not only is the data already in my calculator, I just did my linear regression t-test, and look what it told me. Y equals a plus bx, right? All right, so let me try this again. Here. If I want to get the regression line, let's try again. Let me clear this out. So I have the data in the window. Let me show that to you. Hit Stat, Edit. It's all there. There's list 1 and there's list 2. That's my right arm and my left arm. And I want to express a relationship between the data for both of these. So I go ahead and I hit Stat, go over to Tests. And I'm going to go up again to this linear regression t-test. This is the test I'm using actually for both sections of Chapter 10. I hit Enter. Everything looked fine. X is in list 1, Y is in list 2. Yeah, I'm ready to calculate. Go down here and calculate. Okay, so what's it tell me? It says Y equals A plus BX. Okay? And it says A is 43.56 and B is 1.31. So what can I do now? I can write that down, right? 43.5x plus, or 43.56 plus 1.31x. Yeah, so I guess the notation of our calculator is almost backwards from what it is, what we're used to, right? Because if you look at it, remember how B was the y-intercept? B0 was the y-intercept? But what's the y-intercept in this equation? A. How come? Because B is in front of the x, and if B's in front of the x, what's the number in front of the x called? That's called the slope. You guys with me on that? So that's the slope. So the slope is 1.31x. Yeah. Remember that this is a line going through the sample data, right? Matter of fact, let me show you something you could do with this. It's kind of cool. Press Y equals. And I'm going to type in 43.56 plus 1.31. And now to get the x, I don't know if everyone remembers where to do that. It's next to the alpha key. They have a key that says xt theta n. If you click it, it's going to type an x. That's what you want to do. Next to the alpha key. Now, why did I type it in there? Because I want to look at it. I'm going to now hit the graph button. If you already hit stat plot once, then you could just hit graph. If not, you get stat plot again. But now when I graph, notice what I have. Plot 1 is highlighted on the screen, and the equal sign for this function is highlighted on the screen, so it's going to graph both of them. So if I hit graph, it shows me the data, and it shows me the line going through the data, right? And this is the line that gives me the least amount of what I call error or residual, right? Now this data point missed by quite a bit, But the other ones are all pretty close. This is the best you could possibly do to minimize the amount of error with this data. Yeah? Oh, so I wonder why that happened. Let me see your y equals. Oh, that's weird. Let me see your data. Very strange. .56 plus 1.31x. Is that what we had? I don't know why that happened. See me after. This is what should happen. Something like this. Okay? Oh, one other thing they asked me to do. It says in problem 15, find the best predicted blood pressure in the left arm, given that the blood pressure in the right arm is 100 milligrams of mercury. Okay. Suppose right arm is 100 millimeters of mercury. Now I have to slow down for a second, and I have to decide, when they tell me that, is that my X or is that my Y? That 100. Is that going in for X or is that going in for Y? Well, you can tell a bit by your lists, right? This was X because it was list 1, and this was Y because it was list 2. So the way I did it was X. If someone else did it differently, that's fine. But what you do now is you put that 100 in for the X in the equation. Then you can figure out what y is. So y hat will equal 43.56 plus 1.31 times 100. And you work out what that is. And I guess I'm going to get 163.2 millimeters of mercury. If I round. I'm sorry, what do you say?
If you do the second table and you get the table where it shows out that why would you do it?
Yeah.
It says 175.
Oh, yeah? So let me check this out. 131 plus 43.56. Oh, yeah, I got 174.56. So that's wrong. 174.56 millimeters of mercury. Is that what you got?
175.
Close enough. Okay. So their equation might be slightly different. Let me go back to the calculator and just show this to you. Remember we graphed this equation? 43.56 plus 1.31x. Here's something cool you can do. You have the graph. You know how trace you can move on the data? You can also move on the curve with the trace button until you get to about 100. So there's around 100. We're at about 175. Or another thing you do is you can hit second trace, and it says, what do you want to calculate? I want to calculate a value. So I'll press enter. It says, what do you want x to equal? All right, what do we want x to equal? 100. Enter. There it is, 174.56. So if you already have it in your calculator, this is easy to work with. Yeah, second trace is nice. Okay. So any questions on this kind of stuff? How do you what? Where'd I get the 100 from? Because it, well, you have to decide. It either goes in for X or for Y. So how do I know it goes in for X? Do you see that data? Because look at the original chart. For the original chart, the way I did it was I put the right arm in list 1, and I put the left arm in list 2. And so I made these X's and I made those Y's when I plotted it. So it really comes down to how you plot it. If you plot it the other way, you'll get a different equation, but you could still come up with the right answer to the problem. Yeah. I don't know. Let me do that, because I have no idea. So how are we going to do that? Watch. I'm going to hit. Do you guys understand David's question? David is asking, what would the equation look like if you made the left arm the X's and the right arm the Y's? And I answered him, I don't know. Although I could figure it out in a couple ways. One way you could get it is if you know how to do your algebra, you could solve for that X. Get that by itself, and that'll be the equation. But if you don't like that, another way to do it is, okay, here's what we did. Remember we did stat and we did test, right? Which test did we do? Linear regression t-test. Now, what you were saying is you want the X's to be list 2, the left arm. So I'll do that. And you want the Y's to be L1. So I'll do that. And I'll go ahead and calculate it. Well, that's a very different equation now, isn't it? Because it's negative 2.33 plus 0.57x. All right? That's a very different equation. But I can still type it in the calculator. I could clear this out and type negative 2.33 plus 0.57x. I could still do that. And I could still hit zoom stat, and I will get different points, and I'll get a curve, I'll get a line that goes through them if I did it right. What happened? I don't know. Did I miss my negative? Oh, I didn't change the stat plot. That's the problem. So yeah, you have one more thing to do. We need to make the X's list 2 and the Y's list 1. Probably shouldn't have done this. This wasted a lot of people's time. But we'll look at it now. Okay, and you still get a line through the data. I think, yeah, it was easier to do it the way we did the first time. Yeah. Yeah, then you're fine. Yes, Amber. In problem 15 in the book, are you looking at it, page 549? Oh, that's why. It tells you. It says, hey, find the blood pressure if I tell you that this one's 100. It comes from the problem in the book. Okay.